Hello everyone, this is Mr. Appel, and we're going to look at this example now, which is going to have a little twist to it, so buckle up. Let's graph these inequalities first. So the first one, y less than or equal to x plus 5, it's in slope-intercept form, so I'm going to go ahead and plot the y-intercept there at 5. Slope is positive 1, because it's a 1x, so up 1 over 1, up 1 over 1. And, as I've done before, I'm going to plot a whole bunch of points and go ahead and graph. And 0, 0, plugging that in, that's 0 less than or equal to 5. Wow, that's illegible, but hopefully you can hear me. 0 less than or equal to 5, yep, that works. So I would be shading below, but instead we're going to shade above. So we're going to shade up here because we're shading the opposite. So all that stuff is out. Next one is y greater than or equal to x. If that's confusing, think of it as 1x plus 0. So your y-intercept is 0 and your slope is positive 1. So we're going up 1 over 1, finding a bunch of points by going up 1 over 1, and same in the other direction. Go ahead and graph that line. You should use a ruler. And here we can't plug in 0, 0, but you can pick a point like, 0, 2, which is above the line. And if you plug in 0 for x and 2 for y, that's a true statement. 2 is greater than 0. And so all of these points above that red line should be included in our solution set. So we're going to, again, shade the opposite. So we're going to shade all the points that are not included. The next one, x greater than or equal to negative 3. So that's a vertical line at negative 3, right there on the x-axis. And so there's our x is greater than or equal to negative 3. Again, greater than to the right. I'm going to shade the opposite, which is all of this stuff to the left. And then finally, y plus 2x less than or equal to 5. I'm going to put that one in slope-intercept form. So I'm going to subtract the 2x from both sides. I think that's just going to be a little easier to graph. So our y-intercept is 5 right there. Slope is negative 2, so down 2 over 1, down 2 over 1, down 2 over 1. And I'm going to stop right there because I see right now there's a little problem coming, which is it looks like this green line and that red line are going to intersect somewhere in here, but it's not going to be on a grid line. It's not going to be a whole number. So this is going to be our first chance to see a situation where you really can't easily determine the intersection point, the vertex of the feasible region, by looking at the graph. So to finish that off, the shading is going to be up here because that's all the points that aren't included. And so our feasible region is going to be, let's change that to a color we can see more easily. So our feasible region is going to be right there. Hopefully you can see that. Looks like another trapezoid. So there we go. And so our vertices are mostly going to be easy to read. Looks like this one right here is at negative 3, 2. No problem there. Looks like this one down here is at negative 3, negative 3. No problem there. This one up here is at 0, 5. No problem there. But this one, Houston, we have a problem. That is not a point that's going to be easy to spot. And so the two lines that form that intersection are the line y equals x. So that came from this one. Remember, we're just interested in the boundary lines and where they cross. So y equals x. And then the other one is this green one here, the y equals, well, the original equation, sorry, we'll just use the original before I changed it, is the y plus 2x equals 5. So those are the boundary lines because that's what we're interested in. So we now need to solve this system of equations. We need to know what x and y pair is going to make those two equations true. Well, fortunately, this is a pretty easy system to solve. I'm going to just zoom out for a moment to do that over here. So this one is going to be an easy substitution because y equals x. So in the second equation, I'm simply going to replace y with x. So instead of y plus 2x equals 5, it becomes x plus 2x equals 5. So that becomes 3x equals 5, and so x is 5/3. And even easier, since x is 5/3 and y is x, y is also going to be 5/3. And so that point of intersection that was not easy to read there is, we can determine algebraically, is at 5/3, 5/3. So this is an example where we had to do a little bit of work to determine one of those intersections, but sometimes that is just what must be done. Now we're going to go ahead and evaluate our objective function. So for -3, 2, that's -3 minus 2 times 2, so that's -4. So that's a -7. Here, x is -3, y is -3, so that's -2 times -3 becomes a +6. The next one, x is 0, minus 2 times 5, so that's -10. That gives us a -10. And finally, we get a 5/3 minus 2 times 5/3. And 2 times 5/3, or 2/1 times 5/3, that becomes 10/3. So this becomes 5/3 minus 10/3, which is -5/3, which is -1 2/3. And so we've got some fractions, not a huge big deal. And we can still do the same thing we've been doing. Our maximum value, 3 of those are negative. We have this one, this one, this one, and this one. The only one of those that's not negative is 3, so that's going to be our max, right? Because the positive is bigger than the negatives. And our minimum is going to be the smallest value, which is our -10. So that's all for now. Thanks.